In this video, we will be going through some more examples relating to PV diagrams and talking a little bit more about how we can analyze them graphically to get estimates for different values. So we're going to start off with this first question. To the right is a PV diagram showing the phase behavior for ammonia. So this is a pure component PV diagram. A process starts with 1 kilogram of ammonia, so our total mass is 1 kilogram in a system, and it's contained in a variable volume container, so volume is allowed to change. Initially, the container has a volume of 0.02 meters cubed at a temperature of 580 Kelvin. So use the diagram to answer the following questions. So first I want us to sketch the critical isotherm for the ammonia. So we know our critical point is at the tip of our sloped envelope. So we could just draw that like this. It doesn't have to be perfect, but know the tie line does lie on that part. So this is our critical isotherm. Okay, and initially, what is the specific volume in centimeters per gram? Okay, so this means we're going to have to do some conversions. So V naught equals 0.02 meters cubed, and this is equal to, so we know that there are 100 centimeters in a meter. Then we want to cube that. So this is equal to 0.02 times 100 cubed. This is going to be 20,000 centimeters cubed. We also know that we have 1 kilogram, which is equal to 1,000 grams. So when we put this all together, our specific volume, our initial specific volume, is equal to our 20,000 cm cubed over 3 grams. And this is equal to 20 cm cubed per gram. Part C, the container's volume is held constant as the ammonia is cooled to its saturation point. What is the vapor pressure at this point? Oh, sorry, I missed this one part for B. What is the mass of the ammonia in its liquid phase? Okay, so let's plot this out. We have 20, our specific volume, and at our pressure, we were not given a pressure, were we? Oh yeah, sorry. And then we read up to our given temperature, up to our isotherm of 580 K. And this is our point, this point right here. This is for part B. So looking at our previous notes, I'm going to open it up here really quickly. So looking at our previous notes, we can see that in our bounds, anything that is above the critical isotherm is going to be in a gas state. Oh, sorry. So because of that, that means that everything in here, right? So this is above critical isotherm. So it's completely gas. So that means our mass of ammonia in our liquid phase is 0 because there's no gas present. Sorry, there's no liquid present in the gas. Okay, so our volume is held constant our ammonia is cooled to its saturation point. So what is the vapor pressure of at this point? So for this next question, I'm going to use a different color. So the point that we were given was point B, and we want to cool it. So if we were to cool it, that means we would be going down to the next isotherm, and we want to find its saturation point. So if we read downwards, that brings us to this point here. And when we read across, this is 5 megapascals here. That's about like 5.5 megapascals. So for part D, starting from part C, the volume of the container is reduced at a constant temperature to half of its original volume. So what phases are present? Okay, so volume is reduced, temperature is constant. So along this isotherm, along the dotted line, we are going to have constant temperature. So we want to move along that until our container volume is halved, which would bring us to 10, because half of 20 is 10. So let's read until we get to 10. So we're decreasing our volume, but we're at the same temperature. No, wait, hold on. We stay on that curve, then that brings us to this point here. So for part D. Right, hold on. Sorry, I was also doing this part wrong. Sorry, if we were to follow isothermally up until 10, that means we would just read across, because for each of these lines here, these are each tie lines in our isotherms, right? So now that we're reading to reduce our volume, that means we are also going to read in a tie line fashion up until this point. So we see that point D, is inside the liquid and vapor envelope. So both liquid and vapor are present. Okay, what is the mass of ammonia in the liquid phase at this point in grams? So this is lever rule. So we want to find what it is at each of the edges. So then this is roughly like 0. This is 0. Oh, sorry, no, if this is 5 right here, this is about like 2. And here we were already given our vapor pressure, which we found from part C. Okay, so specific volume of our liquids, about 2 centimeters cubed per gram. We are given V, which we found to be this point here. So that's 10. V vapor is 20. Okay, so we want the mass of the liquid phase. We can make that a ratio, which is equal to vapor minus V V vapor minus V liquid. So then this would be (20 minus 10), and this is 20 minus 2, which is equal to 0.5556, which is equal to mass of liquid over total mass. Our total mass is 1 kilogram. So we multiply that over, then our mass of our liquid phase is 0.5556 kilograms. And we wanted that in grams. So then that is equal to 555.56 grams. Okay, part F, how many degrees of freedom are there at this point? Which intensive variable, if any, is specified by the problem? How many degrees of freedom are remaining? Okay, so in the above statement, our volume was reduced. Actually, no, so, hold on. Okay, so if we just start with our basics for F, so degrees of freedom is equal to our components plus 2 minus our phases, which is equal, so it's a pure component diagram, so there's one component present, plus 2, and minus our phases, which is liquid and vapor, so that is 2. So that gives us 1. Which intensive variable is specified by the problem? That is our specific volume of vapor. And because this is specified, which is already our degrees of freedom, since this is now fixed, then that leaves 0 left. 0 degrees freedom. So that means the system is now completely fixed. Okay, volume of a container is held constant while more ammonia is added at a constant temperature. Ammonia is added until the container only contains saturated liquid. So how much ammonia is added in kilograms? So first thing we're going to want to do is find out where our saturated liquid is going to be occurring. So we previously left off at this point here. And as we decrease our volume, it's going to become liquid, and only at this point right here does it become fully liquid. So this is going to be called point G. And we already know what our specific volume is because that's the same as our V liquid. So let's write that down. Equal to 2 centimeters cubed per gram. And this is equal to then let's convert our grams. So this is going to be 0.002 meters cubed per kilogram. And our volume we can find with our specific volume, Actually, maybe I should write that out differently. So specific volume we know to be equal to our volume per mass, our total mass. So then that's equal to and then if we wanted to find our volume multiplied by the, okay, give me a second. Okay, I'm actually not too sure if this is correct, but the answer key that I'm using says that a volume overall to 0.001 meters cubed. So then using our equation of specific volume, we get that our mass, so this is what we're looking for, is equal to our volume over specific volume. So if we were to do that, we would get 0.001 divided by 0.002, that's 0.5. kilograms. Sorry, that's 0.01. This is meant to be 5 kilograms. And so we need to find out how much we added. So 1 kilogram was already present. So this is our total, right? So if we want to find how much was added, we take 5 minus 1, which is equal to 4. So 4 kilograms were added. Okay, so that is our first problem done. So let's apply some of our same rules that we learned to a second example. Shown to the right is a PV diagram for a newly discovered substance called stuffium. You conduct experiments with stuffium using a variable volume container that is fitted with an injection port. If you inject 250 grams of pure stuffium into completely empty volume container with a starting volume of 1 meter cubed, determine the specific volume at 400 Kelvin. Okay. So let's start what we need to know. So we're given our mass and our volume, so we can find specific volume. So let's convert our 250 grams into kilograms. So 250 divided by 1,000, 0.25 kilograms. So that means our specific volume is going to be 0.25. This is going to be 1 meter cubed, 0.25 kilograms, equal to 4. Now we want to find what our pressure is. So we know we're given 400 Kelvin as our temperature. So let's find the point we just found and then read up to 400. 400's up here. And so it touches the line there. We read across, and that's about 5 atmospheres. Okay, part B. So following part A, you isothermally increase the volume of the container until you have a saturated liquid. So this means you're on the left side of dotted envelope. And determine the pressure. and the specific volume at these conditions. So isothermally increasing means we're going to trace along that 400 K isotherm. So let's highlight where that is. So we're going to trace it until we intersect with the dotted envelope line on the left, which is where we're going to have our saturated liquid, and that's about 4 ATM. If we read down, that's like 4.5 specific volume. So specific volume is 4.5, and our pressure, which we read, was about 4 ATM. Right, and we're increasing the volumes. That's why we read going that way. Okay, following part B, continue to isothermally increase the volume until specific volume is 8 meters squared per kilogram. Determine the phases present and the specific volume of each phase present. Okay. So if we're increasing, we are reading that way. So from here, we want to read until we are at 8 specific volume. And now we're inside the envelope. So we can answer first question. So inside envelope, we have liquid and vapor present. And we want the specific volume of each phase present. So basically, we just want to read until we have saturated liquid or saturated vapor. So that means we are going to also read to the other end of our dotted envelope. This is our vapor, and we already found our V liquid over here from our previous question. So liquid is 4.5 meters cubed per kilogram. And for our vapor, it's about 15. Following part C, you lower the temperature of the contents in the vessel at a constant volume until an additional phase appears. Under these conditions, determine the following. The pressure in kilopascals. Okay, so we want to keep a constant volume. So the point that we just found in part C was this point right here at 8 meters cubed per kilogram. And we want to read until we find a different phase appearing. Okay, so we want to decrease our temperature. So we see as we go down, our temperature gets lower. So we want to read down at a constant volume. So that means we're going to stay at this 8 meters cubed per kilogram. And we read down to this dotted line here. Now, as some of you may know, this dotted line is our triple point line. So we already had liquid and vapor appearing, so we need to wait until a solid appears, and that happens at this point right here. So we want the pressure of that point. It's about like 2.7. It's about 2.7 ATM, and that turns into 273.57 kilopascals. Degrees of freedom present. We know at triple point we have one component because it's pure component diagram, plus 2, and minus our phases present. We have 3, solid, liquid, and vapor. That means we have 0 degrees of freedom. So all of our variables are fixed. Following part D, now you heat the vessel contents while keeping the volume constant, determine the density of the liquid phase present at an equilibrium of 6 atm. So heat the vessel contents, keeping the volume constant. So that's basically what we just did. We're going to do that again in purple. So where we read down, we want to read up this time, and we want to get to a pressure of 6 atmospheres. So at the same volume, read along that same line until we get here. And determine the density of the liquid phase. Okay, so we want our liquid phase, so we want saturated liquid. So that means we are reading to the left side of our dotted line envelope, and we see that's at about 5. So that gives us 5 specific volume. And we know density is just 1 over our specific volume. So that's 1 over 5, which will equal 0.2 kilograms per meters cubed in density. Following from part E, you are told that exactly half the contents in the vessel are vapor phase at equilibrium. Calculate the volume occupied by the vapor phase. So we're going to need a couple things for this question. So you're given that we have 250 grams in the beginning, and we're told half of it is vapor. So then that gives us 125 grams, which equals 0.125 kilograms is in our vapor phase. And from part E, since we're looking for vapor phase, we want to find our specific volume of our vapor. So let's read that from our graph. So going in the other direction, that brings us to 11, right? This is our saturated vapor on our left side of our envelope. So then that is 11 meters cubed per kilogram. And we know that specific volume is volume over mass total, or mass of whatever phase that we're working with. So that means our volume is our specific volume times our mass. So when we do that, that gives volume equals 1.375 meters cubed is occupied by the vapor phase. A couple more questions, let's finish it up. So next we have we empty the vessel completely and set the volume to 0.135 meters cubed. While keeping the volume constant, you place 10 grams of stephium into the vessel. Determine the temperature in the vessel and the amount of each phase present at 6 atm. So the volume is equal to 0.135 meters cubed. The mass is equal to 0.01 kilograms. Pressure is equal to 6 atm. So let's find our temperature. So knowing our volume and our mass, we can find specific volume. So our specific volume is 0.135 meters cubed over 0.01 kilograms, and that's equal to 13.5 meters cubed per kilogram. Then we know our pressure is 6 atm, so let's plot on our graph. So it's 6 atm and 13.5. Let's read up. It brings us to this point here, which lies on our 550K isotherm. So our temperature is 550 Kelvin. And calculate the amount of each phase present. So how would we do that? So single component diagrams, what we can just do, we know that molar mass is equal to mass over moles. So that means if we want to find moles, we could take molar mass times, our mass over our molar mass. So if we did that for our vapor phase, for example, we would do 0.1 kilograms over kilograms per kilomole. Our molar mass was given at the beginning of the question, so that just gives us 0.1 divided by 100, and that's 0.001 kilomoles. And why did we only need to do it for vapor? Well, that's because in this point here, only vapor is present. So only vapor present. Okay, and last step, you decide to isobarically inject stuffium into the vessel while maintaining a constant volume. So determine the mass that you'd need to inject if you want the final equilibrium temperature to be 400 K. So the first thing that I would do is just see what we have. So our volume is already set, so volume is fixed at, so we're given that at the top of our question, 0.135 meters cubed. And we are keeping our pressure the same, so isobaric process, which means that P is equal to 6 atm still from our previous question. And we want to read to our temperature 400 K. So we ended at this point here. I'm going to do this in a different color. So when we read across, so this is where we ended on. We want to read until we hit our 400 isotherm while staying at the same pressure. So then we would read across till we hit this point right here. That's for our 400 isotherm. And if we read down, that's about, let's clean it up a little bit. So if we read down, that's about like 3.5 specific volume. Volume is about 3.5 meters cubed per kilogram. And so we want to find the mass that we would need to inject. So we know specific volume is equal to our volume over mass. Let's isolate for mass to get our mass equal to volume over specific volume. We're given our volume up here, so 0.135 meters cubed over the one we read off of our table. And that's 0.135 divided by 3.5. And that's 0.03857 kilograms. And if we make this equal to grams, this is 38.57 1 grams. But in the beginning of our question, we already had 10 grams in there, so this is our total, right? So we want to find how much we added. So we're going to take 38.571 grams, and we're going to subtract 10 grams, which was given initially. And that means we added 28 grams. This is our final answer. So that brings us to the end of this video, where we covered some example problems for reading PV diagrams. This question dealt a lot more with saturated liquid and saturated vapor, so if you're ever hung up on that, just remember that saturated liquid happens on this side of our envelope and saturated vapor happens on this side. Right, so you can read across from where you're given. We also talked about isothermal and isobaric processes in this example, so also a good thing to review and look over for future questions. Thanks for watching this video. I hope you enjoyed, and I will see you in the next one.